chapter 24 on the wave nature of light. All right, back in 23, we're using lenses and active light, and we have a light, and it produces an image over here on a screen, and we use this ray model of light, which shows light traveling like that. All right, so you have a perfect, if you have an object here, you get a perfect image here with the right lens. So that was the concept of that principle. However, it was discovered in 1600s by Huygens. That, as an example, if you put light through a slit of small size, an example, well, a pretty small light and a very small slit, you would expect if light was a perfect beam coming at you, then what you'd have on the screen would be this, just the light coming through, you'd have exactly that opening. So what if you had a circular here, you'd have a circular light here, and it'd be dark around it. What he discovered instead is that the light actually spread out into, somehow. So light, rather than just passing straight through, actually spread out, what we would call diffraction. And this is the principle of diffraction. And what this meant from other observations of, say, waves, if you have water waves, so if this is water waves coming down, and there's a nice picture in the book of that, of water waves, then what you've seen, if you've watched, is when they come through, they do not just go straight through. What happens is the water waves end up spreading out, right? So it's like this creates it, and they go out, spread out in circles instead of just going straight through. Again, this is the principle of diffraction. So this is with water, waves, and this is the idea of what we call diffraction. So what this means is that light, rather than just being a ray or particles we'll see, is actually has a wave nature to it. So there's this principle of diffraction going on. And we'll also see, we'll get into another thing, it's a principle of interference. Okay. Now we talked about before, back earlier chapters, the other thing we've talked about as far as waves are sound waves. So sound waves travel with the speed of 344 meters per second. And the relationship between speed, wavelength, and frequency is given by that relationship, where that's the wavelength and that's the frequency in cycles per second, so the product gives you the velocity. For light, on the other hand, light travels, as we talked about in chapter 22, with the speed called c of 3 × 10⁸ meters per second. So light is a particle, and it's also a wave. And this is kind of a problem they had as far as that is concerned. All right, so dealing with that, all right, we've had, you know, we talked about light before. We talked about also how I just talked about with Snell's law, which we dealt back in chapter 23 with lenses. All right, so now what we're going to do is look at interference. So I've done the lab part with this, and I'll give you a couple examples here of diffraction, and then we'll go on to there. So let's look at what we have some examples we call double slit interference, and I'll do a couple demonstrations with the actual lasers. So what we have, and you'll get a better idea. All right, so if we have 2 points, so 1 and 2, and light comes through here, it'll create, like the sound waves, light will come out like this. This one will also do the same thing, they'll come out. And there'll be peaks and troughs, so the waves will actually look like this as they come out. And what we'll see is that where these 2 waves add up together, this is what we call constructive interference. And where the waves, where you have a peak, so if you have both of them together, the result will be a wave twice as big. All the peaks will add together, the troughs will add together. All right? Now, on the other hand, if it's shifted by a little bit, and we can look at this down below. So if you have a peak combining with a trough for 1 point, so you got this for number 1, and it's shifted by, let's see, get this right. Then the peak and the trough cancel out, the peak and the trough, and what you end up with, the result is a straight line, and you have nothing. And this is what we call destructive interference. All right. So what we have here is then, and if we go up along the side, what we'll have is in the center, if they're both what we call in phase, or both going at the same speed, then you'll have a positive. And as we go up, we'll end up with destructive interference, because as we go farther up, this bottom one has to go farther to match that one. So at some another point, you'll have a negative, and then if you move up, they'll end up constructing together again, and what you end up is a bright spot, a dim spot, a bright spot, a dim spot, a bright spot, and so on. So it'll actually look like this sort of thing. All right? And this is what we call interference. All right, here's an example of what we call two-slit interference. Notice we got a bright spot in the center. Now on either side, you have a bright spot, then a dim, dark spot, bright, dark, bright. So we see the bright spots are where we have a constructive interference. Where you have the dark spot is where you have destructive interference, where you have the peak of one ray, one slit, interfering with the trough of another slit, and you end up with what we call single slit, double slit interference. All right, so that's what we have here for this one. Of double slit interference, two waves, bright, dim, and where you have constructive interference and destructive interference. Now we're going to do something if we have one slit, single slit, and this is what we call diffraction, right? So for diffraction, instead of, and I'll show a demonstration, if we have a single slit and light passes through, all right, again, like if there was no wave nature to it, you'd expect a single spot here. Well, as you see, is instead of that, we end up with a broad, the light passes and it's spreads out, but it does more than that. It produces a central bright spot, a darker spot, bright, but then it gets dimmer and dimmer on each side as we go farther away. So unlike interference, where you have, relatively speaking, all of them are relatively about the same brightness, the central one is bright and then it gets dimmer and dimmer after that. We can look at this as a way as on a graph of interference, and we have this in the lab. Okay, so we have the lab on interference and diffraction. We have these exact kind of waves as far as that's concerned. So this is the principle of diffraction, and I'll show a demonstration of this next. So that's diffraction. Right? It's caused by a single slit, and it's unavoidable as far as this. Now, the slit width has to be relatively small. If I have a big, wide slit, like say, trying to put a laser through something like that, like a big hole, I mean, you're not, nothing's going to happen. The slit has to be relatively small for this effect to occur. So that's diffraction. Okay. On the other hand, here what we have is what we call single slit diffraction. So what we have here is due to one single slit, and because of the slit size, we have a bright center spot, and we have similar to interference, but this is caused only by the width of the slit itself. Now the width has to be relatively small for this to occur, but this is what we call a single slit diffraction. So normally you would expect without this, so if I take the slit away, this is what you'd have. And you would expect with the slit to have just the light passing through and be a little smaller. So instead of that, we end up with the slit spreading out the beam, much like a water wave passing through a slit, creating diffraction. Basically, the edges are acting somewhat like individual slits. So that's single slit diffraction. And this is due to the fact that dispersion, we look at the electromagnetic spectrum, right? Roy, G, Viv, red, indigo, blue, violet, and the entire spectrum, then what we actually find is that put light, I'll put it this way. We have light shining on a prism, it will get diffracted. It'll be refracted inside, and we'll have is what we call dispersion. So it will bend the blue light the most. I'll just use that. Bend the blue light the most, and bend the red light the least. That's because the index of refraction varies with the wavelength for glass, so you end up with producing a rainbow. So this is where the rainbow comes in as far as that's concerned. Now, it's Isaac Newton who proved that white light, which is composed of all the colors of the rainbow, is actually composed of all the colors of the rainbow, because they thought when they shined white light to a prism, it was something in the glass itself that changed it so that it broke it up into the rainbow. Well, what he did is took the red light, passed it through another prism, and all it did was bend the red light because everything else had already not passed through. And so he showed that white light is made up of all the colors of the rainbow, and it's split up by its principle of dispersion because each wavelength has a different index refraction. As far as it's not much, but it's enough. It's a principle of why rainbows produce color. So rainbow, and I'll do the example here. This works better than anything. Is that rainbow works by so rainbow, you have sunlight passes through, and it does total internal reflection off the back, comes out, spreads out along the way, and comes out as the colors of the rainbow. So you end up with visible of red on top. You're going to see red. So looking at it, you'll see red and then violet. Now this is a single reflection. Another principle is we can have what we call a double rainbow. So if we have light come from the other way, it goes in 1, 2, comes out, it's reversed, so the violet is on top and red. This is a double. So you have 2 reflections. This is 1 reflection. And 1 reflection, this is the main rainbow, and this is the second rainbow, and the colors are reversed. So when you have a very heavy rain, you'll have 1 rainbow, and if it's really heavy, you'll see the second rainbow, and the colors are reversed as far as order is that concerned. So that's principle of dispersion and using refraction and total internal reflection here. So single ray, the brightest one is 1 reflection inside. The second one is 2 reflections. So that's the principle of that. That's section 24.4. So now we're going to go into we are now going to look at diffraction grading. All right, the next thing we're going to do is look at diffraction grading. This is section 24.6. And unlike a slide that has lots of little slits to it, I'm not sure if I can show that. Well, you can see that here. So you can see the little slits here. So the single slit. So there's a single slit here. A diffraction grating, on the other hand, is made up of many slits. In fact, this one has, I'm not sure how many this has. This has 1,000 lines per millimeter. So a single slit, a single slit, we end up with diffraction, which produces broad bright, dark, bright. So single slit. Diffraction grading, on the other hand, has many, many, many slits. I mean, you can't even see it visually, but it's many, 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 many slits per wavelength, and per millimeter, and all of these produce a single, so it's basically you have all these together, and instead of one bright spot, one spread out light, so instead of one spread out light, you end up with, so you can see here, a bright spot in the center, and then a bright spot on the left, and a bright spot on the right. And this is what a diffraction is. And based on that, if we measure the distance from the center to either one of the bright spots on the right, we can actually figure out the wavelength of this laser beam. And so that's what we're going to look at here. So this is diffraction grading. And it turns out the angle, so this is the first one to either side, just like I showed. This is the angle. Then if the distance is D, is distance between slits, then this angle is such that sine theta is equal to lambda over D. So if you know D, which is the slit width, or slit's distance between them, and we know the angle, we can measure the angle, we can measure the wavelength of that light. And an example here is so if you had an example of 1,000 lines per centimeter, that means D is 1 over 1,000 in centimeters, which would be 10 to the minus third centimeters, or D would be 10 to the minus fifth meters. All right? So then, in that case, if we measure the slit width, and this particular one, all right, so I'll do for this particular laser, I can find it again. Okay. I'll estimate this to be about 40 degrees. Okay? So what we have then is, so lambda will be sine theta times d, and d in this case is times d, so that would be sine of 40 degrees times 10 to the minus 5th meters. Which would be 0.64 times 10 to the minus 5th meters, which would be 6.4 times 10 to the minus 5th, 10 to the minus 6th meters. All right, so that's what the wavelength would be. Now, I'm just making this up as a problem. In reality, this is too long. But if I give you D and measure this angle, then you can calculate what the wavelength would be. So for this particular problem of D being 1,000 lines per centimeter, we end up with this answer here. Okay? So that's the diffraction gradient. Where this is a number of lines, so in this case it'd be 1,000 lines per centimeter. It's probably different from that, but that's okay. And that's what we have there. So that's the diffraction gradient. We have the lab that deals with this. And that's okay. Now, so we use a spectroscope, and a spectroscope is example here, and I can bring one up. A spectroscope, like this one. Spectroscope, we send light in through here, passes through the diffraction gradient, and then we visualize it here. And depending on the angle, we measure the angle instead of this crude estimation. We can get a very precise measurement of the angle by, or I can do this, the angle that the light comes in like so, it gets bent, and we can actually measure this angle very precisely, and from there, using this expression, so light comes in here, right, passes through the diffraction gradient, gets, we see a spot over here, you look at it through here, through the little scope, and this is the angle, we easily measure, so sine theta is lambda, lambda over D. Right. Where again, D is the width between each slit, and wavelength is there. So that's the expression for diffraction gradient. Okay. So based on that, we can get the spectrum of any gas, and each of them have their unique spectrum. So that's what we have the lab, what we did on diffraction, interference, and gas spectrum. So the lab on gas spectrum uses diffraction gradient to measure the wavelengths. All right, so that's the last part. We're not going to do anything on interference in thin films. Last thing I'm going to do is on polarization. and talk about that a little bit. So polarization. And we have the lab related to that, which we have. And polarization is based on the fact that light is a transverse wave, unlike a sound wave. But it's not a simple one wave going up. As it's coming towards you, it's vibrating up, it's vibrating sideways, vibrating all different directions during the sunlight. So if you look at this as a single wave going up and down, going that way, as we'd see. But if it's unpolarized, we call unpolarized, then it's actually vibrating in all sorts of directions coming at you. So there's some light coming this way, some light vibrating that way. It's all random directions overall that way. This is what we call unpolarized light. Some light is unpolarized. Now in this case then, what I can do is this is what we call polarizing filter. So what we have is the light passes through, comes out, and it becomes polarized. And we'll see this in the lab. So this so all the light here coming out is unpolarized, coming in the first place, comes out as polarized. Because if I rotate this, notice it doesn't really change much. Because all it's doing is picking up this one, that one. So the intensity is not changing much, because all I'm doing is picking off one and leaving the rest. Now, on the other hand, if I have this, and I put a polarizer behind it, right? Now this one will be polarized relative to that one. As I rotate this around, see how it gets bright? That means both polarizers are in the same direction. And as I rotate it, the light, this one is now perpendicular, so it's blocking all the light from the second one. So these are now perpendicular, and that's what you have. So as I rotate it, it gets brighter again, then it'll get darker again, and so on. And that's the principle of polarization. So how do we deal with that? It turns out we have light of some intensity, right? Then it passes through a polarizer. The polarization I goes as the cosine of the angle squared. So if this is one, so it passes through that one, and then the other one is at an angle like so. The light coming out will be reduced by that much. So say this one comes in at perpendicular, and the other one is at 45 degrees. So if this is at 45 degrees, then this will be just make this 1, just I naught. So I naught times the cosine of 45 degrees squared, and that's equal to I naught times a half, so it'll be 1/2 I naught. If theta is 0, then cosine of 0 is 1, so that'll be 1. If theta is 90 degrees, cosine of 90 is 0. So square, I get 0. All right? So that's how we use polarization in this effect. And Okay. Now one other thing, talk about Polaroid sunglasses. What are the purpose of Polaroid sunglasses? Well, Polaroid sunglasses are such that light reflecting from a bright surface. So if you are driving, you got the bright sun, and you got your car, and the hood, and the sun is reflecting off the car, you're going to see very bright light coming through here. All right? Now, if you have no glasses on, I mean, now you can put on sunglasses that would be dark enough, but you might have a hard time seeing. But what turns out, reflected light is polarized. Meaning sunlight is unpolarized. When it reflects off, it's polarized in one direction. So then if you wear, have polarized sunglasses, you will then block that reflected glare, but still be able to see everything else. So the only thing that will be blocked will be the glare of the okay. So an example here is, say, glare from if glare from this reflected lake, if you put on Polaroid sunglasses, you reduce the glare, you can actually see what's in the lake. And so on the right, as a person, you have Polaroid sunglasses or Polaroid glass blocking the reflected light. Notice how it has almost no effect on the surrounding part, but just on the reflected light, and you can actually see what's in the lake. So that's the principle of polarization, and that's chapter